Are you able to see my screen? You can see it. Okay. A minute. How about now? How about now? Able to see the screen? I'm writing something here. Can you able to see what I'm writing? Hello? Are you able to see what I'm writing here?
Yes, sir.
Okay, nice. Okay, so in case whatever I'm writing here disappears, please just let me know so that we see how we can fix that problem. So guys, we want to look at a branch of chemistry called electrochemistry. And the two words that make up this word. The first word is electro. Hope my handwriting is visible to you. And then the other word is chemistry. So basically, we have the first word here, which is electro. And then the other word is chemistry. So when you're working with electrochemistry, we want to look at how we can use different kind of devices that are going to convert electrical energy to, chemical energy from the word electrochemistry, because the word chemical chemistry here, we're talking about dealing with the kind of chemical reactions, dealing with concentrations, and so the whole branch of electrochemistry is looking at how we can convert chemical energy to electrical energy. That's what we do in electrochemistry. But if you check most of your examination past papers and you check how questions are phrased, we get to focus on only 7 components of electrochemistry. So here, before this lesson comes to an end, I want us to find out how we can deal with what is called the galvanic cell. If I'm very fast, please tell me the galvanic cell. And I want us to look at how we can deal with the half reactions, the half cell reactions. And I also want us to look at how we can deal with the Gibbs free energy, the Gibbs free energy. And I also want us to look at how we can deal with the potential energies. The potential energy or the electromotive force, EFC. Okay. Then the other thing is balancing these half reactions. How do you balance the half reactions when you've been given that such kind of arrangements? So you guys have come across different kind of questions. Let's admit this person. So I'm sure you guys have come across different kind of questions like these, questions like these ones here. I don't know if you're able to see. There's a paper here. You're able to see, right? So what they do is that there's a branch of chemistry called chemical analysis. So at first year, they get to bring questions from chemical analysis. They give you questions from chemical analysis. And they tell you to say define the oxidizing agent, the reducing agents, coefficients of variations, and then they tell you to say from the standard potential of the following half reactions, determine the reaction that will occur and calculate the cell potentials of the reaction. So this is what we're going to look at. By the end of this lesson, we want to make sure that we find means and ways of attempting such kind of questions. How do we work them out? How do you work the half reactions? What do you do when you've been given the half reactions? And then at certain points I've discovered where we make a lot of mistakes, why you're trying to find the E cell values. So I also want to touch that point so that we fully understand how we're supposed to work out such kind of things. Then the last part here I was saying point 5, why you're supposed to know how you're supposed to balance these half reactions, the half cell reactions. And sometimes most of you that have gone through these past papers, you are taught to balance the half reactions in two ways. The first way is the basic medium, and the other way is acidic medium. So we want to fully understand how do you work out that kind of a chemical reaction. Why you've been taught to say balance this chemical reaction in acidic medium, balance this chemical reaction in basic medium. How do you work it out? So before anything here, remember I told you to say when you're looking at electrochemistry, you're looking at how can I use this device that I have here to convert the chemical energy into electrical energy. How do I work it out? That is what we want to look at here. So amongst the devices that I use, we have what is called the galvanic cell. We have what is called the galvanic cell. Okay, I hope we are taking note of whatever is happening here. We have what is called the galvanic cell. So this galvanic cell is something like this. I think most of you have come across such kind of arrangement where you have a transition here, such kind of arrangements. So my main interest here is trying to bring out the key important points that are needed for it, what you need for it to understand from this lesson. So you have what we call here of a porous discs, and then from here you have that connection there, and then you have your plates. Okay, the plates that are here. So I was telling you to say electrochemistry is where you look at different kind of devices that are able to convert two things, which is uh, chemical energy to electrical energy. So we're talking about the chemical energy to what we're calling the electrical energy. And among the devices that do that is what we're calling the galvanic cell. So this galvanic cell is a branch of it's a device that is part of electrochemistry that is able to convert the chemical energy into electrical energy. But how does it work? Um, there are different parts that make up the galvanic cell. Among the parts are what we call the anode, and then the other part is called the cathode. Okay, so the anode here, and this is the cathode. And for most of us that have done electrochemistry, you know that electrons, when they're moving, they move from a certain part going to a different part in the galvanic cell. I think most of you that remember, you know that the electrons move from the anode going to the cathode, right? Isn't it? Uh-huh. You know that the electrons move from the anode going to the cathode. So sometimes you are taught to show the flow of electrons. You know that this is moving from the anode. These are electrons that are moving from here going to the cathode. So when the electrons are moving from the anode going to the cathode now becomes what we call the reducing agent. Comes in what we call the reducing agent. Then the cathode becomes what we're calling the oxidizing agent. And then the other thing that we must understand here is that you know that there's now a flow of electrons moving from the anode this side going to the cathode. This flow of electrons that is happening here, or the driving force that is making these electrons move from the reducing agent going to the oxidizing agent, is what we call the cell potential, okay, or the electromotive force. So there's a force that is enabling these electrons to move from this point here going to the other point there. There's a force that is enabling these electrons to move. So that is what we're calling the potential energy or the electromotive force. So what is important for you to understand here is that you need to know how you're supposed to label these parts. You need to know to say, you need to know how you're supposed to draw the galvanic cell, how you're supposed to draw the galvanic cell in the exams, and you're able to label each part of the galvanic cell to say this part is the anode, this part is the cathode, this is the reducing agent, and this is the oxidizing agent. Also need to understand the flow of electrons. What do they move? So I emphasize again, the electrons in a galvanic cell move from the reducing agent going to the oxidizing agent. The areas here, from the anode going to the what? Going to the cathode. Do we get that? Mhm. Yes. So now, when these things are happening here, the anode is made up of certain components, and the cathode is also made up of different kind of components. You might be given concentrations of certain reactants that are here, and you also might be given concentrations of certain products that are this side. Remember, when I'm talking about a chemical reaction, we're talking about the reactants, and we're also talking about the what? We're talking about the products. So we need to make a clear distinction between what we have at the products and what we need to have at the reactants. What happens at the reducing agent and what happens at the oxidizing agent. The other words that we can use, the other words that we can use when you're trying to refer to the oxidizing agent and the reducing agent. What other words are those? What words are those? The oxidizing agent is also known as what? What happens at the oxidizing agent? We have reduction. Okay? And what happens at the reducing agent? We are having what is called the oxidation. Okay? So sometimes people get to confuse these words. Oxidation, what do we mean by oxidation? And what do we mean by reduction? So I'm going to explain the two words with respect to what we have here in the picture. Remember that these electrons are moving from the anode going to the cathode. So to mean that the anode is losing electrons while the cathode is gaining electrons. So if you are to be asked a question, what happens with oxidation? Do we gain electrons? Do we lose electrons? It is the loss of electrons because you know that oxidation is happening at the anode, and then the cathode here, this is the loss of electrons. That's why we're having reduction. So that is why you make a clear distinction between what oxidation is and reduction. And the other confusion I've also observed over the time is the oxidation number and with respect to the number of electrons, whether it's gaining electrons or losing electrons. So when it comes to oxidation state, the increase in the oxidation state of an atom is referred to as what? Oxidation, yes. So I'll just say important note here so that you know you can make yourselves a clear distinction between what we're talking about here. Please don't make these mistakes. The first one, we're talking about increase in the oxidation number of an atom. So when you just come across this sentence that is talking about the increase in the oxidation number of an atom, we're talking about oxidation. You talk about oxidation. There we go. And then you know to say the anode, that is where the electrons are coming from, going to the cathode. So to mean the anode, that's where we have oxidation, and electrons are being lost there. So loss of electrons is what? Loss of electrons, oxidation. And the opposite will happen with what? Reduction. So with reduction, you know what will happen next here. So with reduction, you know to say it is what a decrease in the oxidation number in the oxidation number. And then reduction also, you can define it in terms of the gain of electrons. The gain of what? Gain of electrons. So please let us not confuse the two words. If you are that kind of a person that has been that kind of a student that has been not making that clear distinction between reduction and oxidation, please know that today that the increase in the oxidation number of an atom is called oxidation, the loss of electrons is called oxidation, and the increase in the decrease in the oxidation number of an atom or a carbon, or an atom is what we're referring to as reduction, and the gain of electrons is what we're referring to as what? As reduction. So whenever you forget these things, just refer to the diagram that is here, the galvanic cell. You know to say at the point of the anode, that is where we have the reducing agent, and that is oxidation. We have loss of electrons. At the cathode, you know that is reduction, that is the oxidizing agent, and we've got the gain of electrons. In fact, I should indicate here as well. This is gain of electrons. So the cathode is gaining electrons, and then here we have what we're calling loss of what? Loss of electrons. So please learn to make that clear distinction. If you know that, you won't be making most of the mistakes that we make sometimes when you are dealing with electrochemistry. So this is the first crucial part. I don't know if people have understood what I'm trying to talk about here. Am I too fast? Okay. So do we understand what is happening here? Okay, nice. So just a quick summary. Remember, when you're talking about electrochemistry, you're talking about two words. The first word is electro, the other word is chemistry. We're talking about finding a device that can convert chemical energy to electrical energy. And these kind of devices, the device that we get to look at here is what we're calling the galvanic cell. In a galvanic cell, it has got many components. We've got the part which is called the anode, and the other part which is called the cathode. The electrons get to move from the anode going to the cathode. The anode is the reducing agent, that is why we have oxidation, and the cathode is the oxidizing agent, that is why we have reduction. And reduction is gain of electrons. Oxidation is loss of electrons. But increase in the oxidation number of an atom is called oxidation, and decrease in the oxidation number of an atom is called reduction. So please, when you're dealing with half reactions, you really have to understand the two words, reduction and oxidation. Do we get that? Did we get that? Nice. So that's the first part I wanted to emphasize. That's the first point I wanted to emphasize. That is the galvanic cell. So if you are taught to draw the galvanic cell, please don't forget to show them the movement of these electrons, and then when you're taught to say, what do we call this entire process? This movement of electrons, this driving force that moves these electrons, what do we call it? We call it the electromotive force, or the cell, or the potential energy. That energy that is being done there is called the potential energy or the electromotive force. So that's the driving force that moves these electrons from the anode going to the cathode. So I was trying to cover four components here. The first part is the galvanic cell, which I think uh, I explained how that part works. And the second part is I want to look at the half reactions. And then I want to talk about the Gibbs-free energy, because whatever is happening here is involving energy. In every chemical reaction, you have the energy there. We have concentrations, and we have the potential energy being done, the flow of electrons, whatever is happening there, it involves energy. So the first part I've covered here, which is the galvanic cell. I hope you have understood how it works and everything that is happening here. So we can now move on to the next thing, the half cell reactions. how do you deal with the half cell reactions? How can you identify to say this half cell reaction is coming from the anode and this cell half reaction is coming from the cathode? How do you understand that and how do you tell that? So now we can move on. I want you to understand that a galvanic cell works as a spontaneous redox reaction. I think most of us have come across the word redox. What does it mean? Anybody to tell me something about the word redox? This word here, redox. Nice, nice, nice. So we'll just divide this thing, this word here. Well, the first RED as reduction, and the other part is what? Oxidation. Just like he put it, we're talking about a chemical reaction that is undergoing both reduction and oxidation. That is what we're talking about here when we talk about the redox reaction. So now, under this galvanic cell, it works as a spontaneous kind of a chemical reaction. It works as a spontaneous device. What do I mean? It uses a spontaneous redox reaction. It uses a spontaneous redox reaction to produce a current that can be used to do work. That can be used to do work. This statement is very important, very significant. It uses a spontaneous redox reaction to produce a current that can be used to do work. What does that mean? What it means is this: a galvanic cell can have a chemical reaction that is undergoing reduction and also undergoing oxidation. And then all the half reactions that are going to be given under the galvanic cell are going to be given as reduction, as half reactions that are already reduced. That's one thing that you must know about the galvanic cell. So let's take, for instance, you've been given something like this. You've been given to say the overall half reaction for a galvanic cell is this. Ion here with 3 electrons. Then you have copper there. And then you have copper here. That's an ion. That's why it's in aqueous form. Plus the other ion here, which is also in aqueous form. Okay. I think most of us have come across such kind of reactions. How do you work it out? So the first thing that I want you to know here is that all these chemical reactions, for a galvanic cell, the chemical reaction is given in reduction form. So you're going to have something like this. You're going to have your ion showing there, which is aqueous there, giving us the ion 2. And then you're going to have your copper there, going to give us the copper 2. I hope you guys are able to see what I'm writing here. And then the other thing that you must know is that these ones here are given the energies. because there's work being done in this movement of electrons, and that work being done is the energy I've been talking about here, the electromotive force or the potential energy. So this is what is happening here. So when you've been given this, then you've been told find out the number of electrons that it took for ion 3 to move to ion 2. Find out the number of electrons that it took for copper here to become copper 2. How do you work out such kind of a thing? So I'll start with the first half reaction. So with the first half reaction, I'll say note. I want you to observe to say you have your copper 3 here. A minute. You have your copper 3 here, and we're forming a copper 2 here. How many electrons are on the side of the reactants? How many electrons are on the side of the reactants? 3 electrons. And how many electrons are on the side of the reactants? Those are 2 electrons. And you want to find out the difference between the 3 and the 2. And you want to make sure that you balance this number of electrons. So if I find the difference between 3 and 2, by the difference I mean you subtract 3 minus 3 from the 2, and then you find that difference of 1. And I want to balance up this chemical reaction. Where am I going to add the 1? Am I going to put it on the side of the reactants where I've got more electrons, or on the side of the products where I've got less electrons? I'm going to put it on the side of the product where there are few electrons. And the 3 from 2 is what? That's a 1. So I only have 1 electron here. So I'm going to put it here. A minute. Are you sure I'm going to put it there? Okay. Let me do that. So when you do that, is this chemical reaction balanced in terms of the number of electrons? It's not balanced. Look at this. I was saying from the side of the reactants, I've got 3 electrons. And on the side of the product, I've got 2 electrons. And when you find the difference between 3 and 2, you're finding a 1. That is 3 minus 2 is giving you a 1. Then I ask you a question. You know that an electron is negatively charged. And when you add it to anything, it subtracts. Because this is a negative charge that it has here. So where am I going to add it? On the side of the products or the side of the reactants? For me to have equal number of electrons on both sides. On the side of the reactant. Very good. So I'm going to add the electrons here. So I'm going to have that plus 1 electron there, then giving us that. So you guys, you know that you have 1 electron here which is negatively charged, and then you have a 3 there. So if you are told to find out the total number of electrons that we have here, you have the 3, and then this is a minus, that's a minus 1. You're going to get a 2. And then how many number of electrons do you have on the side of the product? You have a 2. So you know that now we have equal number of electrons on the side of the product and on the side of the reactants. So the first thing that you look for when you're trying to balance any half reactions, look at the number of look at the atoms. Do I have equal number of atoms? The amount of atoms of ion that I have on the side of the product, is it equal to the number of atoms that I have on the side of the reactants? So you have to also make sure that you balance up that. Then you also look at the electrons. So that's one way you work it out. So this is a balanced half reaction. You have two electrons on the side of the reactants and two electrons on the side of the product. This is a balanced half reaction. We equally do the same for the for the copper. But before I do that, I was saying something here. If you have been given something like this, to say all these half reactions were reduced, so they worked them out. They found out the number of electrons that each were losing or gaining. So then they iterate to say this was given a 2 plus, and then they iterate to say you have a 2 plus here, then this is that, and then which is giving copper here. And then they give it to say the energies that were taking place here are the energy of 0.77 here, and on the side, on the other half reaction, you have the energy of 0.34 volts here, and also these are volts. And then you've been taught to say in a galvanic cell, the half reactions are given in reduction form, so meaning they're already reduced. So whatever we're having here is reduction. And remember what I was talking about reduction, I said decrease in the oxidation number of that atom is what we're calling reduction. An increase in the oxidation number of that atom is what we're calling what? Reduction. So you can see that the oxidation number here is a 2, and then here we have a 0. So we're moving from a bigger number going to a smaller number. That is reduction. The oxidation number here is a 3, and we're moving from a 3 going to a 2. You know that is also what? You know that is also reduction. So now the question is that how do you come up with the overall half reaction for these two half reactions that have been given here? Which one are you going to swap? Because the principles that govern how you're supposed to work with the half reactions, which one are you going to swap? For me to come up with this half reaction, this overall half reaction that has been given here, which one am I? Okay. Why do you say copper should be swapped? Okay, very good, very good. The other point that I can also add on here is that when you've been given the cell potential, just look at the cell potential with the least amount of energy. This is having an energy of 0.77 volts, and this is having this is having the volts, the energy of 0.77, and this is having 0.34. So just look at the one with the least energy, and which is 0.34. So you know you're going to swap this one here. That's one trick that you should also consider, please. When you've been given these half reactions and they're both in reduced state, so you now don't know which one you're supposed to swap for it to come up with one chemical reaction. So just know that just look at the half reaction with the least amount of energy, then swap that chemical reaction. Then there are three things that happen to that chemical reaction that has been swapped. What are those things? Or maybe I should be asking like this. When a half reaction is reversed, what happens to the sign of that half reaction? Okay, it changes. How about when a half reaction is multiplied by an integer? What happens to the E cell of that chemical reaction? Okay, good. It doesn't change. It remains the same. Very true. It doesn't change. So those are things that we must take note. You know that when a half reaction is reversed, when a half reaction has been reversed, is reversed, the sign is also reversed. The sign of the energy is also reversed. So if it was a positive value, it becomes a negative value. If it was a negative value, it becomes a positive value. And this is where I'm going, because I know people tend to make a lot of mistakes, and electrochemistry carries people tend to make a lot of mistakes, and electrochemistry carries a lot of marks. So please, let's take note of that. So the other point is, when a half reaction is multiplied by an integer, the E cell just remains the same. It doesn't change, remains the same. Hope you guys are able to see what I'm writing here. Okay, so I'm going to erase something so that I can just create some space. Okay, so I gave you those two half reactions, and we want to come up with the overall best half reaction. So after reversing those half reactions, you need to have something like this. Remember, we said we're maintaining the first half reaction because it's at the biggest value of energy, and it was like this. That's a 2, and then it had 0.77 volts. And then the other thing here is the other half reaction, which was for copper, it was like this. That's a 2 plus there, plus that, going to give us what? Going to give us copper. And they're going to get 0.34 watts. That's what we had initially. So now you're going to reverse the second half reaction. When you reverse it, you're going to have something like this. So this is copper here. Copper will start first there. It becomes, so we're reversing, the products become the reactants, and the reactants become the products. You're going to have C there. The copper comes there. That's the 2 there. And then I said, what happens to the chemical reaction? What happens to this value here? It's a positive, and because it's a positive, it changes to what? To a negative. This becomes negative 0.34 volts. And then the other one maintains, which is F. That's a 3 plus. These are 2 electrons that are here. And then we're going to be given, which is F, and that's a 2 plus there. And what's the cell? That's 0.77 volts. Now, guys, I want to ask you a question here. Have you noticed that we want to balance this half reaction, want to come up with one half reaction that is going to combine both reduction and oxidation, but the number of electrons for the two half reactions are not balanced. One has a 2 and the other one has a 1. So how can I balance them up? What do we do? This has a 2 and this has a 1. How can we balance up these two, the electrons in both half reactions? Nice, nice, nice. So very good, very good, very good. So the first part you multiply by 1, and the second part you multiply by 2. Why are we doing that? The reason why is because when you multiply 1 throughout the entire course of the first half reaction, the 2 won't change. But if you multiply the 2 throughout the rate of the whole entire reaction here, what will happen is that the 2 are attached to the number of electrons here, and then we're going to have the rest being attached like that, and we're going to maintain the number of atoms for each. So 1 throughout there, that's the first half reaction there, going to give us copper there, plus the 2 is going to maintain. And the second one are going to have 2 atoms of copper plus 2 electrons of copper, going to give us 2 atoms of copper with the 2 atoms of what? With the 2 electrons, they're still maintained, just like that. So now we see that these are balanced. The number of electrons are balanced, and the number of atoms for each half reactions are balanced. So what do you do here? You can now group them, right? So I'm going to add what we have on the side of the reactants with the reactants. I'm going to add what we have on the side of the products with the products. So I'm going to then cancel these half reactions, because you know they will subtract. They will just have to cancel off. This goes off and that goes off. So now the reactants with the reactants and the products with the products. So what you have here is copper plus the 2 here, 3 plus, and then on the other side you have the 2 plus there, plus the 2 atoms of what? Of copper. So when you find out to say the number of atoms for each half reaction are not balanced, or when you come up with one equation that just like the one we've done here, and then you discover to say atoms are not balanced, electrons are not balanced, then you've made a mistake somewhere. So please make sure that you check your work. So we have 1 atom of copper here, 1 atom of copper there, 2 atoms of iron here, and 2 atoms of iron there, and the number of electrons are also balanced. So this is how it works out. And if you check the previous reaction that we had, it was the exact same thing. It was the exact same thing. That's what we had there, right? So guys, this is how it works out, and this is how you're supposed to work out this entire chemical reaction. So this is how you work out the half reactions. And then the other part that I wanted us to discuss is where you're supposed to find the cell potential, because this is the part where we make a lot of mistakes. When you're finding the cell potential of a half reaction, or between 2 half reactions, you know that these 2 half reactions, we have the energies that have been given. For the copper, we had negative 0. We had a positive value, which was 0.34 before it was reversed. And then we had a positive value for the copper, which was 0.77. And when you're finding the E cell, this is the formula for it. So say the E cell value is the cathode minus the anode. If you don't want to say cathode minus the anode, you know what happens at the anode, at the cathode, and you know what happens at the cathode, and you know what happens at the anode. At the cathode, that is why we have what? The oxidizing agent. That's why we have reduction. And at the anode, that's why we have what? The reducing agent, also oxidation. So we want to find out which one was undergoing reduction and which one was undergoing oxidation. But initially, we knew that these half reactions that were given here were both reduced. So by reduction, I mean the first half reaction for iron, it was reduced. And the second half reaction for copper, it was also reduced. But what did we do? What did we do? So if this was undergoing, if the first half reaction is undergoing reduction, and we swap the other one, what is it going to undergo? The opposite. No, oxidation. Remember that we're trying to come up with a redox reaction. One reaction undergoing reduction, and the other reaction undergoing oxidation. So you know that this is a 3. We're moving from a 3 going to a 2, and we're moving from a bigger number going to a smaller number, and that is reduction. But after reversing this chemical reaction, we're moving from a 0 here. This is the reversed reaction. We're moving from copper here, which has got an oxidation number of 0, and we now moving to a 2. We're moving from a smaller number to a bigger number. That is what we're calling what? Oxidation. So you now know which half reaction is happening at the cathode, and you know which half reaction is happening at the anode. So reduction here, that's the cathode, and oxidation. Oxidation, that's what? That's the anode. So when we get back to our formula here, the cathode, we have our value there. What value do we have at the cathode there? 0.77. 7 volts. Now here, this is where the tricky part comes in. And this is why people make a lot of mistakes. Please get me here. Please get me. On the side of the anode, you're going to find different kind of situations where you're going to be required to subtract or to add such kind of arrangements where you're supposed to find the E cell of that half reaction. But what governs you? What must lead you? You know that the first part here is called the anode, the cathode. We have no problem with this part. It's okay. We have our value there, which is 0.77. And then the second part here is negative anode. So this negative is part of the anode. So it moves as a whole. It moves like that. And you know what to say, that part of the anode, we initially were the negative number, we had the positive number. This is what we had at the side of the anode before it was reversed. In fact, it wasn't even specified by then if it was the anode or it was the cathode. What the value which was a positive value, which was 0.34. So after reversing that chemical reaction, what happened is that the sign changed. It now became a negative number. So it now became this. It became negative 0.34. So this is the anode here, which is negative anode. So what you do is this. After reversing that chemical reaction, this value became a positive value. So you take it as a whole. You just take it the way it is here. Leave out this negative because it means that the negative 0.34 is replacing the negative anode. So I'm just going to put negative 0.34. The mistakes that some of us used to make is that we used to say, okay, this is the anode and the negative remains there, and then I'll just add negative 0.34. Then negative 0.34, negative times negative, it gives you a positive value. So then you'll end up adding the two values and then you get a wrong answer. So it doesn't work like that. So carry it as a whole thing. You carry the anode part, then you transfer it part of the equation, then find the difference there. So the answer becomes 0.77. You subtract from 0.34. So what value are you going to get there? You're going to get 0.43 volts. And that's the answer here. That's the E cell they're looking for. So they'll mark you for three things: balancing those half reactions, coming up with one over a reaction, and then also finding the E cell. So please avoid making mistakes when it comes to finding the E cell of that half reaction. I hope I got myself right. I don't know, you guys, if you have any questions here. Okay, I was saying that before this chemical reaction was reversed, it was a positive value. We had 0.34. After reversing this chemical reaction, we had negative 0.34. So when you're adding this negative, you're adding the negative to the energy here, and it becomes negative 0.34. So this negative 0.34, you're not going to add it on the part of the anode just as negative 0.34. It's going to replace this part which is together with the negative anode. Okay? So the cathode is already a positive value there. You know that to say the negative is not with the anode, it's not with the cathode, the negative is with the anode. This negative value here, this negative here, it is with the anode, it is not with the cathode. So whatever happens here at the side of the anode will affect whatever is happening here. So this value that we got here was a negative value, so nothing will change. It's still going to maintain the same thing. We're still going to have a negative value there. It won't change to a positive because you're going to say negative here because that other one became a negative, negative times negative getting a positive value. It doesn't work like that. You just get it as a whole thing. Since this was a negative value, okay, still maintains here. You put it as a negative value. You're going to see the other example I'm going to give you that also differentiates the two things, because you get to see how it becomes a positive value and how it becomes a negative value. So if this was a negative value, in fact, if we say initially we're given negative 0.34. If initially we're given negative 0.34, then you reverse that chemical reaction, it becomes 0.34. Then you know we're not going to subtract here. We're going to add because we're taking it as a whole, because this is positive 0.34 at the end of the anode. Let me make myself clear. Okay. Any other questions? Am I very fast? Okay. So guys, this is how you work it out. Please don't make mistakes when it comes to finding the E cell. And the E cell carries quite a number of good marks. So the anode here, remember, it is a negative anode. So whatever changes here, it also changes right here. But not just getting the value, but you get the sign as well. This is a negative value. Initially it was a positive value. After reversing the chemical reaction, it was a negative value. We now have negative 0.34, which comes there. If it was a positive value, if it was a negative value, it would have been a positive value. And all that would have put here would have been a positive value, would have been saying 0.77 plus 0.34, and we're going to get our final answer there. So guys, this is how it works. Please avoid making mistakes when it comes to finding the E cell. I hope you guys won't be making these mistakes. Anyways, we'll look at more examples and we're going to see how we can work them out as well. More examination past papers. Okay? So that's how you find the E cell, and that is how you balance up these half reactions. So this is my guide. I've covered the galvanic cell here. I've also covered the half cell reactions. Then how you are supposed to find the potential energy or the EC of that chemical reaction, and then the Gibbs-free energy. That's what I'm supposed to look at here, and then you are going to finish up with balancing these half reactions. The Gibbs-free energy is something very easy, because they just tell you to say find out the work that was taking place here, because it is found in joules. And when you're talking about the joules, they're asking you what amount of work did it take to move these electrons from the anode going to the cathode. What amount of work did it take for it to find out the rate of this half reaction or the rate of the other half reaction? They're looking at the amount of work, and it must be found in joules. And that is why it brings up the aspect of two chemical reactions: a spontaneous chemical reaction and a non-spontaneous chemical reaction. So the formula for Gibbs-free energy is this: negative N F, then the E cell. And the bad part about this equation is that when you've been taught to find the Gibbs-free energy, so let's say for instance you've been given this question and they're saying balance these half reactions, find the E cell, and then find the Gibbs-free energy. So if you got the half reaction wrong, you're going to get the if you get the half reaction wrong, you're going to get the value of the E cell wrong. And if you get the value of the E cell wrong, you're going to get the Gibbs-free energy wrong as well, because you're going to put the wrong value here. And when you put the wrong value here, it means that even the Gibbs-free energy becomes a wrong answer. So we need to make sure that we do the right thing. It is only by doing the right thing that you get to better results. So in the Gibbs-free energy, The N is standing for the number for the atoms, the reacting moles. They're asking you, in that half reaction that you are balancing, what value was balancing up? What number of electrons were balancing up those two half reactions? So if you look at this half reaction that we had here, what value was balancing up the two half reactions? It was a 2. Thank you. Thank you for that. It was a 2. That's a vibrant voice there. That's -2. Then the Faraday constant. This one says, I think from our secondary school, we knew what the Faraday constant is. It is a value which is 96,400 and what? 85 coulombs per mole. So that is -2 times 96,485. Then you multiply it by the E cell that you found, which is 0.43, okay, volts. And we know that when you multiply this value here, this is a negative, this is a negative. So it means that the entire value you're going to get here will be a negative value. So if the Gibbs free energy is negative, the kind of a reaction that you're having there is a non-spontaneous kind of a chemical reaction. It means the half reactions of that chemical reaction did not balance up, okay? That's a non-spontaneous kind of a chemical reaction. A negative half reaction, why I've got the Gibbs free energy as a negative value, that's a non-spontaneous kind of a chemical reaction because the Gibbs free energy is what? Is negative. So this is a non-spontaneous chemical reaction. Sometimes they'll ask you, what kind of a reaction is it? Why? Because they're looking at it from the aspect of the Gibbs free energy. Since the Gibbs free energy is negative, that's a non-spontaneous chemical reaction. So if you found the value, okay, maybe I ask this question. What can make this chemical reaction spontaneous half reaction? By what means can we get a positive value here as our Gibbs free energy? Okay, when the E cell value is what? No. Yes. So uh when the E cell is negative, non-spontaneous kind of a chemical reaction. We're saying when the E cell is a negative value, uh, when delta G is negative. But the question is that what Gibbs free energy are you getting? Uh-huh, uh-huh. That's what you remember. Okay. So what makes a spontaneous reaction? Okay. Okay. Nice. So maybe I say if the Gibbs free energy is less than zero, what kind of a reaction is this? Spontaneous reaction. And then when the Gibbs free energy is equal to zero, what's that called? Not really, because because the reaction is what? Is at equilibrium. Yeah, because the reaction is reversible. Then you are talking about an equilibrium reaction. And then when delta G is less than zero, that's a negative value. What are you going to have there? I mean, greater than zero. That is a nice spontaneous chemical reaction. It requires energy. It requires energy, external energy for that matter. Okay, so that is what we're talking about here. So we're saying when delta G is less than zero, that is a spontaneous kind of a chemical reaction because the gap-free energy is a negative value. So that was a mistake there. Oh, I was writing. Okay, I was writing nine spontaneous here. So, oh, okay, I see your point. I see your point. So when delta G is less than zero, you're going to get a negative value. That is going to give you a spontaneous kind of a chemical reaction because it requires internal energy. It doesn't require external energy. And when delta G is equal to zero, they're saying that chemical reaction is at equilibrium. And when delta G is greater than zero, and that is a spontaneous kind of a chemical reaction. Are we together? Okay, nice. So, so guys, that's how you're supposed to find the work. We're looking at the amount, and then don't forget the SI units. This is found in joules. It's found in joules. So you find out that value, then you're able to make those conclusions. So questions come like that, and you're supposed to break them out with respect to that in that man. Okay, are we together? And then the last part that I want to talk about is the part where I look at the concentrations, because in every chemical reaction, remember that you're talking about the concentrations of these chemical reactions, the components, the species of that chemical reaction have got concentration. So now, what equation can we use when you're trying to make that relation between the E cell values with our concentrations? So there are two half reactions, that there are two equations that we use. The first equation is this. The first equation is E is equal to the E cell minus 0.0591 over N trying to find out what's the energy of that chemical reaction, 0.0 of that half reaction, 0.059 over N log Q. The other reaction that you're going to be given is E cell 0.0591 over N log K. Maybe some of you might be asking to say, what's the difference between the two formulas that you've given us here? The difference is that one is happening at equilibrium and the other reaction is not happening at equilibrium. So, which reaction is happening at equilibrium here? If you look at the two half reactions, which one is happening at equilibrium? So, when the half reaction is at equilibrium, then you can use this one here. And remember, what I was saying here is that when that half reaction is at equilibrium, you know to say the delta G of that chemical reaction is equal to 0. So that reaction is going to occur. The reaction is reversible because it is at equilibrium. And then while you're using this formula here where you're finding the energy, just know that you've got the E cell here, 0.059 over the N. The N is the balance in mole ratio equation, the balance in mole ratio. Then the log Q. Log Q, we're talking about the products, the concentrations of the products over the reactants. So this is what it means. We're talking about 0.0591 over N log. We're talking about the concentrations of the product over the concentrations of the reactants. So you'll be given the concentrations and you have to work them out. And that's how you work out such kind of equations. So guys, the key things I wanted to emphasize here when you're dealing with electrochemistry, uh, how you work out these half reactions, how you balance these half reactions, how you find the delta G, and how you interpret that delta G if it's a spontaneous kind of a chemical reaction, an unspontaneous chemical reaction. If that chemical reaction is happening at equilibrium, you really have to understand this thing. So basically, this is what it is about electrochemistry. The other part is why I want us to talk about how we can find the these chemical reactions, acidic media, basic media, and so on and so forth. But before that, yes, yes, this is a Q here. That's the first equation I've given. Instead of log, it's lean. Okay, you can give me A. Uh-huh, uh-huh, uh-huh. Okay, uh-huh. Oh, you mean this one here? Okay, and there's no difference between these equations that are here because the R is a constant, it's a value, the gas constant of that chemical reaction. And all these chemical reactions happen at a certain temperature, which is 25 degrees. Okay, so the standard conditions of these chemical reactions are 25 degrees. Yeah, it depends on the questions because when you use this equation here, let's take for instance, I'm telling you to say no, it's not happening at 25 degrees, then it means that you have to change the temperature here. Then the gas temperature is that's a constant value. I think you've come across things where you'll be given these values. The value of R, you'll be given that value. You know the Faraday constant that's a constant value, you know it and how it works. So you just have to divide that, then you'll be able to get to this point. If it's happening at 25 degrees, you'll be able to get back to this point. So it's just entirely dependent on the temperature. But normally, in all your questions, they all happen at 25 degrees room temperature. Most welcome. So guys, this is what it is about electrochemistry. Then before that, I wanted us to look at this question here. Okay, look at this question here. I want us to learn something from this question. Are you able to see it? Are you able to see? Okay. The question is saying, from the standard potentials of the following half reactions, determine the reaction that will occur and calculate the cell potential from the reaction. So they're saying, come up with the overall half reaction from these half reactions that have been given here and find out the cell potential. But again, we're going to proceed further because we want to find out because we've been given everything here. So let's find out what we can do here. So, guys, what's the first thing from from the work I've given you? What are we going to do for it? What's the first thing we're going to do from here? What are we going to do? Okay, we balance the half reactions. Okay, how many chlorine atoms do we have on the side of the product for the first half reaction? Okay, nice. Let me just write it here. That is PT Cl6. Then you have that plus 2 there. Then giving us PT Cl4. Then you have that plus 2Cl. You have that. So I say the first thing that we do is balance this half reaction. How many of PT atoms are one here? PT atoms are one there. What else do we have here? 6 atoms of chlorine, 6 atoms of chlorine on the side of the product. So the atoms are balanced. What do we look at next? Yes, we look at the electrons. On the side of the reactants, how many electrons are there? How many electrons are on the side of the reactants?